Hello everyone, this is Dr. Webb. In this video we're going to look at two new coordinate systems for 3 dimensions that often are useful for using in integrals. Really, one of these, cylindrical, this is only sort of new. You've seen all the components before, we're just packaging it up in a new way. Spherical coordinates, on the other hand, that's something that's going to be much more new. So let's start off with cylindrical coordinates. Okay. So in cylindrical coordinates, we're going from our normal x, y, and z to the coordinates r, theta, and z. And you've seen r, theta, and z before. So if you notice, z's there, z stays the same. R and theta we saw before in the polar coordinates, and they mean the same thing here. So these are the same r and theta from polar coordinates. And so really in this change of variables, really it's x and y is going to r and theta, and z is just staying the same. Z stays the same. Okay, so we've seen all these conversions before. So x turns into r cosine theta, y turns into r sine theta, z stays as z. R is equal to the square root of x squared plus y squared, theta is equal to arctangent yz, and z is equal to z. So, we want to draw a picture of this. If we're looking at some point where we go out x over y and up z, and so this is x, y, z, well, thinking about this in polar, we're going out r, sweeping over theta, so this is r sweeping out theta, so r is still on the xy plane, and then z staying exactly the same. So we're still just going up z. Okay. So cylindrical coordinates, these naturally are quite useful in carving out cylinders, and so that's kind of where the name comes from. You can kind of see as we drew this out, we kind of cut out kind of part of the cylinder here. Okay. And with integration, especially in two variables, the big question is what happens to area when you change coordinates. So now that turns into, in triple integration, what happens to volume when you switch to cylindrical coordinates. And so we're really talking about what is dv supposed to equal now when we have things in cylindrical coordinates. Well, remember that dv is dx, dy, and dz in some order, right? Well, what's dx, dy together? That's area on the xy plane. And so we can think about dv in terms of x, y, and z as being area on the xy plane times dz is representing height to give us volume. And so dv is dA dz, and we know what dA is in polar. So in polar, dA equals r d theta. Right? So plugging that in, that's going to give us what dv is for cylindrical coordinates. So this r d theta, that's dA, dz is dz. Okay, so let's do an example. Let's use cylindrical coordinates to set up the integral, which represents the volume of the solid inside the cylinder, x squared plus y squared equals 1, between the xy plane and the plane z plus x equals 2. Okay, so remember from our last video that volume is equal to just integrating the surface, just integrating dv over the surface. Okay, so we just need to figure out these bounds. The xy plane, that z equals to 0. This plane right here, we can think of as being z is equal to 2 minus x. And so this is already set up nicely to integrate in terms of z first. Let's do a quick sketch of what this is going to look like. So we're looking at the volume inside the solid, inside the cylinder, x squared plus y squared equals 1. So that's just drawing out the unit circle on the xy plane, and then the cylinder goes up and down from there. Then it has the bottom of the cylinder is going to be the xy plane, and so that's our base. Okay, and then the plane z plus x equals 2, or z equals 2 minus x. So on the zx plane, if I put a mark down for 2, the slope is then going to go down, hit 2 over there. And so this is going to hit the cylinder somewhere around there, and then kind of, I think, cut out kind of like an ellipse on the top. Right, so this kind of looks like what you have if you have a bar and slice it at sort of a 45-degree angle, I think. Okay. And so that's our volume there. So if we're going to integrate z first, we're thinking about if I take some spot on the xy plane, and then I'm integrating from the xy plane, so that's z equals 0, up until I hit the plane on the top. So my z values here, my z values are going from 0 until I hit the plane, which is at 2 minus x. Okay, but I want to do this in cylindrical, and so what is x equal to in cylindrical? Well, x becomes r cosine theta. So my bounds for z are 0 and 2 minus r cosine theta. Okay, and so now we're thinking about the dA part. So integrating over the unit circle. Well, we've done the unit circle in polar before, and we can think about the unit circle as being, it's a unit, so the radius is going out to 1, and theta is going from 0 to 2 pi. So the way we have this set up, it looks like we have this kind of written, we're going to integrate z first, and then we're going to do r or theta in some order. It doesn't really matter because neither of them depends on the other one in these bounds. Okay, and so our integral is going to become, so we're just integrating dv, and so in this case dv is we're integrating z first, and the integral from z is 0 to 2 minus r cosine theta. And it's okay to have r and theta in the bounds here because they're going to be integrated later. Then let's do, for dv, I need r in here. And then let's do r next. R is going from 0 to 1. And then lastly, let's do theta. So 0 to 2 pi. And this would be a pretty quick integral to do. Pretty quick for triple integral, which means it would probably only take about 5-6 minutes to do. So one thing, be careful of, make sure you have that r there, because you need that r there to make this whole thing dv. Okay, so that's an example of cylindrical coordinates. Again, with everything in triple integrals, this takes some practice to do. But generally in cylindrical coordinates, what you want to do is you think about integrating z the same as you did before, and then the region on the xy plane is some part of a circle, and so it makes sense to switch that into polar. Okay, spherical coordinates. So spherical coordinates, this is a bit of a different animal. Okay, so if we go back to our XYZ space, to have some point in XYZ coordinates. So there's my point XYZ. Okay. So we're going to rewrite it in different coordinates, and so the names of these are the first one that looks kind of like a script P. This is called rho. It's a Greek letter rho, and looks kind of like the handwriting way of looking at it looks kind of like that. The main difference between it and a P is that when you write it, you start from the bottom and then loop up and do it. So it looks a little bit different than your normal P, where you kind of start down and go through like that. Theta, you've seen theta before. Turns out this is the same theta you've seen before. And then the last one is the Greek letter phi. So this is sort of the normal printing way of writing it. Handwriting, it's often written like that. And so this is equivalent to that. This sort of one super loop way, that's the faster script way of writing it than the circle with a line through it. Okay, so where are these? So rho, it's like, has an R sound, kind of like radius, but it's not radius on the XY plane, it's actually the radius out from the origin. And so it's a spherical radius, which just means that it's the distance from the origin. So rho is that distance from the origin. Theta is the same thing. So it's the angle you went out from the x-axis above the xy plane. That's theta. And then the last one, phi, is another angle, but this angle is it's an angle coming down from the positive z-axis. So phi is that angle right there that you came down from the positive z-axis to the point. So if phi is equal to 0, that means that is going up the positive z-axis. If phi is pi over 2, so that's going down 90 degrees from the positive z-axis, then you're on the xy plane. Okay. And so to some degree you can think about theta and rho are kind of talking about longitude and latitude in on a globe. The big difference is phi. When you're talking about latitude, usually you think about the equator being 0 degrees. Phi's sort of the complementary angle to that. At phi, the North Pole would be 0 degrees. The equator would be pi over 2, and the South Pole would be pi. Okay, so let's write these out. So phi, it's the distance from the origin, and so rho is the distance from the origin, and so rho is always going to be at least 0 or bigger. Theta, the same theta as in polar. It's the angle on the xy plane out from the x-axis, and so usually theta is going to go from 0 to 2 pi or minus pi to pi, depending on what you need. Phi is the angle down from the positive z-axis, so it is an angle of declination down from the positive z-axis, and phi only goes from 0 to pi, because once you get to pi, then you're all the way down to the South Pole. You don't need to go back the other way because theta going around to 2 pi is what gets you the backside. So one big thing to note, the angle theta goes, the length of its interval is 2 pi. For phi, the length of its interval is only pi. Okay, and so it's a big difference between these two angles. Similarly, if you think about longitude and latitude on the globe, your longitudes go from essentially minus 180 degrees to 180 degrees, so 360 degrees. But latitude just goes from positive 90 to negative 90, so only 180 degrees. Same thing here. Theta, it's like the longitude, goes all the way around 2 pi. Phi, it's like latitude, only goes from 0 to pi. Okay, so in terms of doing conversions to cylindrical coordinates, it's actually easiest to go through conversions to spherical coordinates. It's actually easiest to go through cylindrical coordinates. Cylindrical coordinates, it's sort of like a halfway point between rectangular coordinates and spherical coordinates. Okay, and so if we're thinking about these coordinates in going from polar to spherical, so remember in polar, if you have some point, you go out theta, out r, and then up z. Okay, well, when we do this in spherical, theta is going to stay the same. So rho, r, and z make a right triangle, and so let's kind of rewrite this right triangle over here. So in this right triangle, the rho side is in blue. It's going to be the hypotenuse. The base is r. The height is z. And so this is going to give us that rho squared is equal to r squared plus z squared. So rho is going to be the square root of r squared plus z squared. And then we can rewrite this triangle and copy this r right there. And the reason why I'm doing that, so really I'm drawing this r back to the z-axis. The reason I'm doing that is because the angle phi is this angle right here on that right triangle. So there's our phi. So let's rewrite that one. So if that's z, that's r, that's my rho. Phi is that angle right there. And so r is opposite phi, so sine phi is going to be r over rho, r over rho, but really if we're doing this between r and z, r is opposite, z is adjacent, and so tangent of phi is r over z. Okay, and lastly theta, that's equal to theta, and so these three right here are really what's giving us our conversions. So rho is the square root of r squared plus z squared, theta stays as theta, and phi is going to be our tangent of r over z. Okay, now going the other way, so what if you have rho and there's r, that's z, and that's phi again. And so this is the This is the triangle that we saw before. So now we can use the fact that r is opposite of phi, and so rho times sine phi is going to give us r. Z is the adjacent side, so rho cosine phi is going to give us z, and theta still stays as theta. And so that's our conversion back from spherical to cylindrical. So r is rho sine phi, theta is theta, and z is rho cosine phi. Okay, so now that we have this conversion into cylindrical, now we can use that we know what cylindrical is to get things in terms of x, y, and z. So what do I mean by that? So rho is equal to the square root of r squared plus z squared. Well, r squared, that is x squared plus y squared. So rho in rectangular is distance formula, square root of x squared plus y squared plus z squared. Okay, theta is equal to theta, but theta in polar is the arctan of y over z, and so that stays the same. Okay, and phi we got as being the arctan of r over z, and again we're going to use that r is equal to square root of x squared plus y squared, and so then that's going to give us that phi is the square root of x squared plus y squared over z. Okay, what about going the other way? So x in cylindrical is r cosine theta. Well, r, we figured out, is rho sine phi, and so plug that in, we get that x is rho sine phi cosine theta, so rho sine phi, that's r, and then cosine theta is still there. Y is r sine theta, and so again plugging in rho sine phi for r, we get rho sine theta sine phi for y. Last but not least, z is just r cosine phi. We already figured that out before. Okay, so here are our conversions into spherical. Okay, so spherical, the name, you can think about r because it's carving out distance. It very naturally and easily carves out parts of spheres. And so that's where the name comes from. And so for this example, let's use spherical coordinates to give bounds for the solid that's above the xy plane. It's inside the sphere, x squared plus y squared plus z squared equals 4. And underneath the cone, z equals square root of 3 times x squared plus y squared. Okay, so let's start off with the sphere. So this is a sphere of radius 2. Let's use black. Okay, and we're just doing this down to the xy plane. Okay, so the sphere, it's out 2, curving out like this, back around, going up 2, coming out like that. Okay. Now this cone, z is equal to square root of 3x squared y squared. It actually might be helpful to see what this cone looks like. We can use the fact that x squared plus y squared equals r squared. We can see that this is really z is equal to r times square root of 3. And so if you think about this, so this is sort of rotating around in a circle. And so on either the xz plane or the yz plane, it's going to carve out a line of slope square root of 3. And that's going to swing around in a circle. And so it kind of curves, cuts out that right there. Okay, and so our surface looks, our solid looks a bit like this. Okay, and so what it is it's think about it as a ball with a cone cut out from the top. So it's a top half of a ball. This cone part is cut out. And so if I want to look at, let's focus in on what sort of one cross section. So focus in on this sort of one cross section right there. That one slice right there. And because this slice is sort of being swung around the z-axis to give us our shape. Well, this slice is looking like this, where this side is on the XY plane. This is the outside of the sphere, and the sphere is radius 2, and so this right here in terms of spherical coordinates is rho equals to 2. Okay, and then this top part right here, well, that's this coming from this line with slope square root of 3. And so if we want to get our phi here, so the z-axis was pointing straight up from here. So phi is that angle sitting in right there. So remember, phi is arctan of r over z. And so if I want to get r over z, this is going to be 1 over square root of 3. And so phi is the arctan of 1 over square root of 3. And so this angle phi right here where it's starting is at, so this is pi over 6. And then phi then is going down until we hit the xy plane, and the xy plane, that's at pi over 2. Okay? So let's write out our bounds. So rho, we're going from the origin out to 2. So rho is going from 0 to 2. Our phi bounds, we're going from starting at pi over 6 and then angling, keep going down until we get to pi over 2. So phi is going from pi over 6 to pi over 2, and then theta, we're going all the way around the xy plane. So theta is going from 0 to 2 pi. Okay. And so, you know, if you think about this, if you tried to do this in either rectangular coordinates or even in cylindrical coordinates, you'd have to break this up into multiple solids to put this together. However, in well, there's one way in cylindrical in which you wouldn't have to cut this up, but it still wouldn't be pretty. However, in spherical coordinates, not only do you get to do it in one piece, the bounds, they look like rectangular bounds. They don't depend on anything, so you could integrate this when we get to the point of integrating it in any order you want, and it's going to work out nicely. Okay, so, but to do integration, we got to do the same thing that we did in cylindrical coordinates. We have to figure out what volume is going to be in spherical coordinates. And so the picture for this would not be real pretty and may not help very much. And so instead of doing the picture, let's do a 3-variable Jacobian. Okay, so we're going to calculate out the Jacobian from here. Now the Jacobian in 3 variables, it's complete analog of the Jacobian in 2 variables. Remember, to do the Jacobian in 2 variables, it was the determinant of a 2 by 2 matrix. So to do the Jacobian in 3 variables, it's going to be a 3 by 3 matrix. Okay, and so we need to know what each of these are. So X is rho cosine theta sine phi. Y is rho sine theta sine phi. And Z is rho cosine phi. Okay, now we need all the partial derivatives. So let's do these out. So partial of X in terms of rho is going to be cosine theta sine phi. Partial of X in terms of theta is going to be minus rho sine theta sine phi, and the partial of X in terms of phi is going to be rho cosine theta cosine phi. And then let's do the same thing for Y. dy d rho is going to be sine theta sine phi. dy d theta is going to be rho cosine theta sine phi. And then dy d phi is going to be rho sine theta cosine phi. And then last but not least, Z, it's not cosine. Yeah, it is Z cosine phi. And so dz is is just cosine phi d rho. Then dz d theta is equal to, there's no thetas here, so that's just equal to 0. And then last but not least, dz d phi is going to be minus rho sine phi. So now that we have all of our partial derivatives, we can pile this into the matrix and take the determinant. So, flump, there it is. So the way that I did this, this is the X column, the Y column, the Z column, and then this is the rho, the theta rho, and the phi rho. And so remember this you can take transposes and it doesn't affect anything. So that's how this is laid out. So obviously I don't have space here to write out this determinant. So let's just skip to what it is. So if you go through and multiply this out, and actually the easiest way to multiply this out is to use, say, this column, because it has a 0 in it. And so if you expand upon that column, you get this beautiful thing for what you get when you multiply it out. So you can see that everything is going to have a rho squared in it. So you can pull out a rho squared. Everything is also going to have a minus sign, so you can actually pull out a minus rho squared. And then what you're left with, well, if you look in here, there's actually an awful lot of cancellation. So, or simplification. So we've got a sine phi, cosine phi, sine phi, cosine phi, and then they're getting multiplied by, this one's getting multiplied by sine squared, this one's getting multiplied by cosine squared. And so this half right here actually turns into cosine phi on the outside times sine phi, cosine phi. Okay. Same thing over on the other side. We've got sine phi squared, and then it's getting multiplied by cosine squared plus sine squared. And so this half turns into sine phi times sine squared phi. Okay. And so I've got a sine phi times sine squared phi. I'm actually going to keep it like that. From this whole term over here, it's a cosine phi times sine phi. Well, I'm going to move one cosine over and get cosine squared. And now we have another cosine squared plus sine squared. This time I can factor out the sine phi. And so this whole thing right here is going to simplify down to just sine phi. Okay. And so our Jacobian is minus rho squared sine phi. Remember, with Jacobians, we're going to end up taking the absolute value of this. Right? And so this is saying that dv is the absolute value of the Jacobian. So rho squared sine phi times d rho d theta d phi in some order. Okay. So dv is rho squared sine phi times d phi d theta d phi. Okay, so now let's go back to the example we saw before, and let's actually set it up as an integral. So from before, we had our bounds were rho is going from 0 to 2. Phi was going from pi over 6 down to the xy plane, which is pi over 2. And theta is going from 0 to 2 pi. And so putting this together as an integral, well, we have to integrate rho squared sine phi. And so then let's do rho first. So 0 to 2. And then we're integrating, let's do phi next. Pi over 6 to pi over 2. And then lastly, integrating theta, 0 to 2 pi. And so this right here is going to give us our volume. Okay, and so remember this rho squared sine phi, this is important because this whole thing, or I don't forget the d theta at the end, that whole thing in there is just dv. And so we are integrating just dv here, but the bounds are so nice, and rho squared sine phi, that's not a bad function to integrate. And so this actually would be quite a quick triple integral, so maybe only 7 or 8 minutes to actually go through and do. Okay, that is all I have for you for this video. I will see you again soon.